Hello, I'm Sam, and in this video I'll be talking about the inductance solver that comes with ElectroMag Nodes under the advanced category. This solver is only available in the Pro version of ElectroMag Nodes. So with an empty scene, we'll start by deleting everything, and let's drag and drop this solver in our scene and see what we get. So what this solver does is allows us to calculate the inductance of a certain coil, and the way it does this is uses a simulation node. So let's bring in our timeline and let's just run this quickly and see what we get. Press play, and you see this plane starts to move upwards, starts to scan the inductance, and it gives us this value of 13.35 microhenries for this toroid. This is an air core. This is an air core toroid. Let's go back to the beginning and let's talk about what we have here exactly. So we have three objects that come with this node. The first object comes with a curve that we would like to. This curve is the original curve of our coil that we designed, um, and then it comes with another object called the winding visualizer. Is basically what it does. It adds thickness to the curve and such that we can see it properly. And the third object is the inductance solver, and this is the one that calculates the inductance. And the way this works, if we bring in wireframe mode, essentially it's similar to the 2D plane that comes that we the 2D plane or the arrow grid. And the way it works is that it calculates the magnetic field at each frame and it moves up by one step, moves upwards, and then it sums up all the energy, and that's how it calculates the inductance of any coil. If we have a look at the inductance solver, the geometry uh, modifier panel for it, and see what options we have. First option is the target coil, and that's what coil we want to measure its inductance. The second option is the size of this plane. Now this plane should be slightly larger than the coil itself. We don't want to make it too small, and we don't want to make it too large either. If we show the wireframe, and you can see that if you make this too large, then these sampling the vertices in this plane will be more spaced apart, and that will impact your accuracy. I did find a value about 1.25 to be a good value that gives me good results. Number of vertices is the number of vertices in this plane. So if we make it bigger, we get more sampling points. Naturally, if you have a larger size, you do want to make have more vertices to get better accuracy. I also found a number of 50 vertices to be a good number, a good balance between accuracy and speed. And the resolution is the resolution of the curve of the coil that we're sampling. And the last option is the wire radius, which is the radius of the wire of the coil, and this is a very important parameter. The inductance will change according to the wire radius. There's also a second modifier, which is the inductance label, and that deals with the inductance value that's displayed. And it's also in this modifier where you specify the units. So you can either choose between meters if it's unchecked or centimeters once you check if you check the value. So if our coil was in centimeters, then the inductance will be 133 nanohenry. If it was in meters, it would be 13.35 microhenries. If we run the simulation again, you'll notice, and if I stop it just about here, you'll see that how this plane turns white. This color white essentially is the magnetic field strength. So you would expect the field strength to be um, strong for the toroid inside the toroid. And this could be used as an indication as to where to place the plane initially. So if you have a different coil, you might want to place this plane further away um, or further closer to it. Um, First thing I would do is at the first frame, move this plane in the z direction until you just about see the field, or for first indication that there's the field becomes strong, which is just about here. And then you would run the simulation, and then you can stop it once the field disappears. So you might be asking, how accurate is this result? And the best thing to do is, well, you can either build the coil and take measurements, or you can use a professional simulation tool to compare this result. And for that, I'll be using FastHenry for it. FastHenry is also a free tool. It's quite an old tool now, was initially developed in the 1990s from MIT. You can download it from fastfieldsolvers.com. And this is the exact same coil that we have in Blender. I'll be talking about how to export your Blender coils and curves into fast field solvers via FreeCAD. And so let's run this simulation in FastHenry and see what we get. So the simulation is running, and we get our results very quickly because we've chosen low frequency. Frequency at 1 Hertz, we get a resistance value and a inductance value. The inductance value given is 1.35 to the power 5 minus 5, which is 13.5 microhenries. And if you compare that to our result in Blender, it was 13.32. So it's not far off. Now perhaps might be a good opportunity to see what happens if we increase the number of vertices, the points that we're sampling in our inductance plane, and see how close we get to FastHenry. So let's run the simulation again with 75 points. It's running a bit slower now, but you can see now we've got 13.4 microhenry, so we are getting closer to it. And also we could try and perhaps increase or decrease the plane field and see how that will impact the result. So let's run the simulation again. So now the sampling points are closer to each other and a bit lower, 13.35 microhenries. Now let's have a look at another coil example. So I've got here a spiral, and this could be a PCB coil. This coil was initially designed in Inkscape, and I just imported it into Blender. So first of all, I'm going to grab my winding visualizer, and I'm going to select my PCB spiral. This is what it is, and I'm going to keep the radius of 0.01. Now the coil is going to be in centimeters, so we will change the units once we set up our inductance solver. Let's bring our inductance solver closer to the center, pressing Alt G. And let's also make sure we're targeting the winding visualizer, which is also targeting the PCB spiral. And let's go back down here and set our units to centimeters. The wire radius for the PCB coil radius is 0.01 centimeters, which is 0.1 millimeters. Now, PCB coils won't have a circular cross-section. It's more of a rectangular cross-section. Now, in this version of ElectroMag Nodes, it only supports circular cross-sections. I hope in the future I'll be able to change that to include any type of cross-section. So I think now we're all set up. Now let's have a look at our inductance plane. You can see now it's turned all white, which means that this plane on frame 1 is too close to the coil. So let's move it away in the Z direction, move it down until the field becomes weak or barely visible, which is just about here perhaps. And let's look at the top view, and let's make our coil also the plane bigger. So let's go with try 1.5. I think that should be sufficient. And let's still have 50 vertices, and let's run the simulation and see what values we get. It's running at 17 frames per second, and stopping it right here, we get a value of 606 nanohenries. And a similar thing, let's compare this with our result in FastHenry. And if we bring up FastHenry, this is our PCB coil. Also exported from Blender directly. And let's run our simulation in FastHenry and see what we get. Where's our result? Our result is right here. And Again, at the low frequency of 1 Hertz, we have a resistance value and a inductance value, and you can see it's 594 nanohenries. And if we compare that again to what Blender gave us, 606 nanohenries. And let's also try a similar thing where we um, increase the number of vertices, see what we get. Again, it's running a bit slower now. And you can see now it's almost it's 597, and again compared to 594, so very close to FastHenry. And so now we've used we've designed two coils, a toroid and a spiral, and we've compared our results with FastHenry. Now, just want to mention that this tool is still in its early phases, and so I would not use this tool to rely on this tool to design inductors. You only perhaps just use it as a starting point, as a guidance, and then once you have a certain coil that you think it's worth proceeding with, you then go to a professional tool to confirm your simulation results. Now, in the actual file that you download, I've also included a few other coils for you to try, and I've also mentioned what is the result that I got in FastHenry. So, although this one here is the main asset, you can still try these ones. So, if you want to try this PCB inductor and see what the inductance we get with it, it says here unit is in centimeters, and the wide radius is 0.0135, and this is the inductance result we got in FastHenry. So if we just take our inductance solver plane and let's just go to top view, and let's just make sure we bring it here, and let's also target this coil here, and we're in frame 1. Let's bring our plane up in the Z direction until we just about see the field, so just about here. And I think the actual size of it is okay. So let's change the wire radius. So it should be 0.035, and we are in centimeters. So let's run the simulation, and we are getting about 57.73 nanohenries compared to 58.1 nanohenries in FastHenry. I should note that I've noticed that the accuracy gets worse if you have a low number of turns. So if we try the single turn um, example, and I've noticed that the accuracy does get is not great when you have low number of turns. So let's target this single turn, and radius is still the same, and we are in centimeters. Let's increase it just about here. Perhaps we could shrink it a little bit, maybe. And so let's see what we get. Not too bad, 9.07 nanohenries. The location of the FastHenry files, I will be placing a link for them in the documentation, so you can download all the FastHenry files and verify these results. One thing also I'd like to point out is that in all of these examples so far, you notice that all the coils have been uh, in this orientation. There's no need for them to be in this orientation. In fact, if we take our circle again and if we just rotate it in any random direction, the result will change slightly, but not by huge amounts. So let's try this again. And we got 9.15 nanohenry. So it could be in any in any rotation.